Right. This is the graph of the student school. We are going to cover uncertainty in this video. So, what is uncertainty? What are the different types of it, and how we calculate in different scenarios? We are going to cover all this in one video. So, let's start with what is uncertainty and errors. So, there are two kinds of errors that we usually make while making any measurements in an experiment. So, there is a systematic error and there is a random error. The systematic error is a fixed shift. Okay. So usually what is error? It is basically how you are deviated from the true value. So if the deviation from the true value, if the shift is fixed, then that's a systematic error. If your deviation from the actual value is varying, so that is a random error. Usually systematic error is caused by a fault in instrument or a method of investigation, while a random error can be a human error. It can be by the method of how the observer is taking this reading, that can be also involved in random error. Now, in systematic error can be reduced by if you calibrate your instrument correctly or change your method so that you can minimize this systematic error. In random error, what we do is we take multiple readings and we take average of those readings to minimize a random error. Now, there is one more quantity that is called as accuracy and precision. Accuracy indicates how close the readings are to the actual true value of the that what we are measuring, and precision relates to how close the values that we are measuring are with respect to each other. How close are they? So, in a given, if I give you an example, imagine an experiment if I'm plotting. So there is a reading which is actually true value. But if I'm measuring different data, if I'm connecting different data points, my graph must be spread out, okay, around that value. So this particular value scenario is high accurate because you can see that the mean or the peak of this particular data is very close to the actual value. So this is high accuracy, if I will say. But since the graph is spread out too much, it will be low precision. Okay. Similarly, if I have a true value again, but my data is now not much spread out and exactly above. So this is the situation of having high accuracy and high precision. Okay. So one more example I can give you. Imagine you have a peak, but it is slightly away from the actual value. So this is like high precision, but it is low accuracy. Similarly, I can draw a scenario with your graph is spread out too much and it is the uncertainty is somewhere away from it. So this is a situation of low accuracy and low precision. Okay, so I hope you understand. Now, how those accuracy and precisions are related to systematic and random error. So when you correct your instrument, you are correcting the accuracy of the instrument so that you will get closer to the actual value. So this will be, so as you reduce systematic error, what you are reducing is like you are improving your accuracy. Correct? Now, we can say that as we reduce random error, what we are doing is we are improving our precision. Okay. So in a graph, if I'm taking this readings, if I take a reading, my graph is supposed to be passing through origin. If it is passing through a deviated plot, but the values are very much closer to the straight line of best fit. So this is a situation of like it is low accuracy because it is away from the origin and it is high precision. Okay. But if the graph is passing through origin, but the values are completely away from the line, okay, then this is a situation of like high accuracy but low precision. In the graph as well, we can detect this. Now, we'll talk about uncertainty. Now, uncertainty is basically is present in any experiment that we take by instrument or by human error. Now, this particular uncertainty is represented like, so there is a true or null value and then there is the uncertainty, that is what we call as absolute uncertainty of x. Now we have different forms of uncertainty like fractional uncertainty, where we take the uncertainty, absolute uncertainty divided with the true or the mean value. And percentage uncertainty is also written as like this. So we take just multiply it with 100 and we will get a percentage uncertainty. Now, if the data is given in form of, let's say, if I'm measuring some values like x is given, like this. In this case, what I will say is that there are multiple readings. How can I find this? So first, I will define the mean value. That will be my x naught. So I will add those values and divide by 4. Okay. And so that's my mean value. While you can get the uncertainty by taking the max reading, the max value and the minimum value, and then divide it by 2. So here we can see that the max value is 10.4, while the minimum value is 10.21. We can take that. So that's how we can find, and finally I can write my answer in form of this. Okay. Now, then we have multiple variables involved in our given data. What we can do is we have something like called as propagation of uncertainty, where imagine there are A and B as a variable whose uncertainties and actual values are given. Then what we can do is if there is some other variable that is related to a sum or a difference of those two variables, we will just take a sum of the uncertainty to find the uncertainty in Q. And we can find the true value by taking the sum of or difference of that true value. Okay, so we can see that whether it is addition or subtraction, we always add the uncertainty. Okay, so that is something that we can remember about this. If we are multiplying or dividing, we rely on finding the fractional uncertainty areas. So first we can find the true value or the mean value by taking the mean values product or division, and then we can find the fractional uncertainty by using this formula. If there are powers to any variables that we want to involve, then we can just take that power in front of the fractional uncertainty. But also there is a mod sign. The mod sign indicates that whether the power is negative or positive, we always may multiply it in numerator. So whether it is n raised to -2 or a raised to 2, we will always take it as 2. Okay, and then not a negative number. So and we have to know that if there is a square root of a raised to n, we can write this as basically 1 by a raised to n. So 1 by n will come in denominator, and we have to remember we have to take the positive value only. Okay. Now I will give an example because this is where if you so let's say there is a variable that is time period. Time period is given by 2 pi root of L by G. So there are two variables L and G. So L is length and G is the acceleration due to gravity. So if I want to find the uncertainty in T, so since there is a multiplication division involved, I can take the values and take the fractional uncertainty. And you can see that the square root is also sometimes can be written as like 1 by 1 over 2. So first thing that we have to remember, we don't take constants in our uncertainty. We are only want to take the uncertainty of the variables. So delta L over L, but here I will multiply it 1 over 2. Okay. So similarly, since they are dividing, I will take the uncertainty of G as well, since both are under square root. So like this. So what if you have something like a parameter of a rectangle? For a parameter of rectangle, you have to measure the length and the breadth twice. So the formula goes like 2 times length and breadth. Now here I will specifically take the parameter and I will answer. So since there is addition and subtraction, I will add the length uncertainty twice and the breadth uncertainty twice. Now we will see that here also 2 is a constant. So why I'm taking it twice? Because in a parameter you are required to measure the length twice, okay, and the breadth is twice. So the measurements that are involved. So you have to count how many measurements you are taking. So that many uncertainty you have to multiply. Okay, not like constant like this 2 pi, which are outcome of a formula. Now we can say that there is one more I will example I will use. So imagine you have acceleration which is given like this, and M1 and M2 are two masses, and G is also acceleration due to gravity, and we are supposed to find acceleration and uncertainty in E. So what we can do is first we can find A naught by putting in the actual values in that formula, and we will get the A naught. But you can treat the numerator here as a whole term. So this will be like uncertainty in M1 minus M2 upon M1 minus M2 plus we will take M1 plus M2 upon M1 plus M2, and then we have delta G upon G. Now how we can find M delta M1 minus M2? So since it is subtraction, we will just add the uncertainty of M1 and M2 like that. Similarly, if it is M1 plus M2, we can take this. Okay. So this is how we do if there are multiple terms in numerator, adding or subtracting. Okay. Now I will also give you an example where uh, a variable like a formula is given something like uh, I is equal to, let's say, 1 upon a plus x the whole square. Okay. Now in this particular case, if a is a constant, if they are so a is a constant, and if I want to predict this uncertainty of I, so I will take uncertainty of I upon I. So since there is a power of 2, and if it is known in denominator, I can write this in numerator. It will be minus 2, but we don't take minus sign. So it will be just 2 times uncertainty of a plus x upon a plus x. Okay. Now we can find uncertainty of a plus x by taking uncertainty of a and uncertainty of x. You can see the difference how we can usually find different values and uncertainty of that. Another part of this particular topic is writing the line of best fit. So usually in a graph, what we do is if there are points with an uncertainty given. So what we plot is along with the points. So these are the points. So let's say I have y variable and y is given as some point and uncertainty in that y value. Now in that case, this y point will be my y naught actual value, and this is 2 times the uncertainty. So the plus and minus. So this is how we do it. It can be in the x variable also. Okay, but this time this will be 2 times delta x. Okay, so this is how we plot. Now, if I want to plot a line of best fit, the rule for the line of the best fit is the line of best fit should be smooth. So smooth line means that like things like this, it should be either a smooth curve, a straight line, or something like that. Okay. Second, it should be passing through all the error bars. Okay. Passing through error bars. Okay. So imagine if I have, so you have a region through which the line of best fit can pass. So I will make sure that it passes through like this. Now you can see that there are multiple ways to draw a line of best fit for a given graph with an uncertainty. So what we usually do is we, along with the line of best fit, so if this is a line of best fit, we will find a slope that is k naught. So that's a gradient. Okay. So since there are multiple lines possible, what we also do is like we can take a gradient, like a line which passes through the bottom of first and first point and the topmost point. So that will have a k max. That's the gradient. So k max will be the gradient of line with max slope. Okay, gradient of line width. So you will see that that's the point which have a maximum slope. Then Then what we can also plot a point from line from the top of the first and passing through bottom of the last point. So that will be okay. And we can find the uncertainty in gradient by taking max minus minimum and dividing it by 2. So this is how we do it. Now usually if there are some non-linear function that is given, like for example, if they have given p is equal to uh, p naught upon the root of b. Now, and if they ask you to plot a graph of P and B, now obviously the graph will something be non-linear. That won't help us to find this unknown value. So usually what we can do is basically uh, you can plot value of P and 1 upon square root of B. So you can say that you can convert. So equation of straight line passing through origin is like this. So you will get a straight line passing through origin, the slope that will be equal to like that. So choosing correct variables to plot on each axis and correct form of them is also very crucial. Okay, this will help you to find the correct value of slope and the constant that are involved. Okay, so this is how we do. I will give you one more example on that. So I is equal to some c upon a plus x the whole square. Now let's say I and x are the two variables. So I will convert this equation. Let's say I will multiply this. I will plot one upon x. So I will plot one upon x square on one axis and I on the axis, and this I will get in slope. That is c. Okay. So usually remember the what is the equation of a straight line, what is the y-intercept, and how we find plot uncertainty. Now, uncertainty may be constant, may not be constant in given situation. So, for a given point, if the uncertainty is very, so for example, if this point has a more uncertainty as compared to other, and then what we usually look for the uncertainty at a particular point only. So, for that point, the uncertainty are calculated from the graph only. Okay. So those are mainly the topics involved in uncertainty. I hope you understood. Okay, thank you so much.